talk about the title of the talk today as Embodied Intelligence from Autonomous Experience, which I'll introduce more later, and maybe go to the third slide. So yeah, I work on robot learning. I am both a final year PhD at UC Berkeley and also a visiting researcher at Meta. And when it comes to my research, I develop real robot systems, and with work spanning dexterous manipulation, local manipulation, and whole body control. And also I draw from a wide range of data sources and learning-based methods. So my work has covered approaches including teleoperation, Toru, and learning from videos. And for learning methods, I also work with imitation learning as well as reinforcement learning. Okay, next. You figure out the play. Okay. So for today's agenda, as the title suggests, I'll be talking about learning from autonomous experience. So I will start by talking about what exactly it is and why we should care. And then link to the core challenges that I think and how my research resolves some of the challenges. And then finally, there will be time for Q&A. But also, as mentioned, feel free to interrupt anytime. So we see a lot of recent advances. I think all of us are aware of all the large language models happening, also great video generation models, as well as most recently a bunch of advances in robotics. We're seeing a lot of humanoids doing different tasks like folding clothes, making coffee, and making boxes. We also have autonomous driving car running on the road of San Francisco. Next. So the standard recipe today, if you think about all these advances, is basically converging. Everyone is using big data and supervised learning. And this is basically mimicking human behaviors. Next. But if you think about it more carefully, none of this is actually Peter lesson pewed. And what is Peter lesson? I guess I don't need an introduction for this. And I also recommend this video between Rich Sutton and a great podcaster on why he thinks about none of this is Peter lesson pewed. So I won't go into more details here. And I will just mention one important reason why I mentioned this, because what is the Peter lesson? It basically says long-term progress should come from methods that scale effectively with compute. And that's clearly not the case with the current approach that we're taking. If you look at this survey from the year of 2023, it was already saying that high quality data was running out. And it's just even more so the case today. And that is just when it comes to large language models. If you think about the harder modalities, like robotics, the data is only getting more expensive and more scarce. Next. And another thing that I want all of us to think about is how differently humans and animals really learn. So compared to the currently popular paradigm of learning from big data, we learn in a fundamentally different way, which is from experience autonomously. So if you observe how children learn in general, you see a fundamentally different process where there's a lot of active interaction with the world. They're guided by rewards and goals rather than these teleoperated trajectories. And in the first place, there is no such thing as teleoperated data from another embodiment. Every one of us learn from a very personalized and very interactive experience with the environment. So going back to why the previous approach was not Peter lesson pewed and why this one could be another promising way. If you think about it, our own interactive experience with the world can give us infinite in-domain data, and it basically leads to a chain of never-ending learning. And of course, this will lead to long-term scalability. It also happens that there exists a natural algorithmic framework that already fits into the story, which is reinforcement learning. So I'll talk more about it later today. Next. So now I've gone over what learning from autonomous experiences, why is it important. I'll just go straight to the core challenges in my research. Next. So again, I'm going to talk more about RL. Hopefully I don't need to cover more basics of it. and I'll just skip this part. So assuming that everyone have a basic understanding of what RL is, if you think about RL application into robotics, there are a lot of natural technical challenges that arise in this process. That's also quite different from the case with large language models or videos models. First of all, there's the hardware bottleneck. This means that all the RL application to robotics is bounded by real-world time and also real-world hardware. One person can only operate one hardware at a time. You can't really do a lot of parallelization for data collection, like how you do with collection of text data and training of text data. And that means the data is scarce. And it also means exploration in the sense of RL is going to be really expensive because you can't have a hardware just running 24 hours a day. It will just start breaking the environment and also breaking itself. And also lastly, for robotics, there's something interesting that I don't see many people discussing, which is that the objective here is hard to define. There isn't anything universal like the transformer objective. And it's basically a question with no clear answer. Next. Yeah, so given these technical challenges, naturally, well, what's our hope? So our key question is how to build practical robot systems that only need a small amount of data, can learn from autonomous exploration efficiently, and with generalizable task objectives. So this is our vision, and now I will talk more about how my research addresses some of these challenges here. Yeah, linking to different parts of my publication, which I will go over now. Next. So the first challenge, exploration from scratch, is very hard. Next. So what is exploration? It just means that in the basic reinforcement learning loop, you need some way to get your own experience to begin with. And that process of exploring the world to get your experience for learning is called exploration. And why is it hard to explore from scratch? Because for us, for children in general, we can learn fast from autonomous trial and errors because we have the biological structures and instincts that's built in from evolution to protect us for safety and also just guide us for exploration. So immediately we know there are these things, these surfaces that we need to touch, and they're this kind of motion that we want to use. But for robotics, this is definitely not the case. If you just throw in a bunch of random weights and let it start exploring from there, the outcome is going to be catastrophic. So how do we fast track this evolution process in robotics? Next. So one way that one of my previous research work proposed is to simply collect multisensory policies from human guidance. So in the simplest term, this is basically a very intuitive teleoperation interface that allowed us to quickly collect a lot of data with a complex robot system that come with a human-like form. You can see in this picture, we use 2 Euro-5 arms equipped with 2 multi-finger hands so that it basically looks like an upper torso of a human body. And given that, we connected with a VR headset teleop. So basically, one person with no prior experience in data collection can just quickly ramp up and collect 100 trajectories within an hour or so. Next. So having this set up give us just really fancy teleoperation capabilities to the extent that we can use a simple VR headset to teleoperate the robot, to even play a game on a controller. So now you can see how this tool can allow us to collect a lot of data for diverse household tasks and train dexterous manipulation policies from there. Next. Yeah, so this is an example of 4 policies that we trained with the data collected on this setup and also with the tactile sensor on the fingertip. So all these are autonomous policy played at 1x speed. Next. Yeah, and building on top of this, we also extend this setup to perform more challenging tasks on more challenging humanoid embodiment, doing things like dishwasher loading and also whiteboard wiping. Yeah, so going back to the challenge that we were tackling, as I mentioned, exploration from scratch is not easy on this real robot hardware. So basically with these teleoperation interfaces and policy learning from multisensory data, we're able to fast track evolution by just quickly ramping up the robot to these basic command skills. So next, I'll go into this second challenge of defining a learning environment and reward. So for this part, I'll actually go into the RL challenges. Next. So if you think about how humans and animals learn, our sensory motor skills really evolve from one, a complex and well-designed world, and second, a clear objective of survival. And how are we going to translate it to robots? How do we design a world for them to actually learn skills that are useful to us? And how do we define objectives that can be numerically optimized other than just saying the simple survival as goal? So in this section, I'll present my work that touches upon practical RL with some Toru methods. Next. So first work I want to introduce is this publication we have at Cohere 2024 titled Twisting Lids Off with Two Hands. The TLDR in this is we train two robot hands to twist bottle lids using purely deep reinforcement learning and Centauro. And the result is dexterous and robust and generalizable behaviors that is from a scalable approach. Next. So just an overview of what this whole pipeline is about when I talk about Centauro RL. So on a high level, it's pretty straightforward. You have a definition of the design, you have a reward design, you have definition of the task, you choose a simulator you like, for example, Isaac Gym in our case. You learn the policy somehow in the simulator, and then you deploy it in the real world. And for this, we're completely dealing with lowest level of control. So the observation is just proprioception and object state, and the action is also the low-level torque commands. Next. So on the first glance, it sounds really easy, but as I mentioned, there are a lot of practical challenges when it comes to engineering this whole world and reward for successfully completing these kind of robotic tasks. And the first challenge is physical modeling. And in this case specifically, a very natural question for physical modeling is, how do you model a bottle? How do you model the complex twisting joints that's on the bottle cap, between the bottle cap and the bottle thread? So traditionally, there was a really hard graphics problem. And in our case, we found that instead of directly tackling the faithful modeling problem, we can use a more hacky way, hacky but work, by simulating the pressure you get when you try to twist open or twist or close the bottle lid. So here, I'm not sure how familiar the audience is with Isaac Gym, but basically you can define this artificial joint in Isaac Gym so that it allows you to add artificial force to any rigid bodies of choice. And that will allow us to simulate bottle twisting without solving the graphics problem. And next. So another challenge that we ran into is how to design rewards for this task. So in a lot of prior robotics work, the reward design were a lot more similar, a lot more simple, because first of all, the dimensionality of the robots are much lower. People used to use the 7 dove arms with a single parallel jaw gripper. But in our case, you can see, even though there are only 2 hands, each hand is already 16 degrees of freedom, which makes them 32 degrees of freedom in total. This is already close to some of the humanoids. And with this kind of high-dimensional robot embodiment, designing the right reward becomes a lot more tricky. So it becomes even harder because the task itself is not that straightforward. Like, how do you define numerical reward for twisting bottle lids? And in this work, and also in the next work that I will introduce, we realized that there's actually a universal formula for defining a lot of reward for manipulation tasks, because you can decompose manipulation as basically two things. One is the contact state, which means whatever your finger is coming into contact with some part of the object that you're handling. And the other one is object state, which is whatever velocity or position you want your object to be at. So by combining just these two terms, the contact reward and the object state reward, we propose this really general recipe for defining reward for tasks ranging from twisting, and later on you'll see things like handover, picking up, and other manipulation tasks. Next. And finally, just another slide on the challenges with Toru. So as mentioned, you need to first train a policy in simulator and transfer it to the real world. But the biggest challenge here actually lies between the gap in simulation and real world. For example, in the real world, we can easily set up a camera to point at the scene and capture videos of whatever robots and objects that you're handling. But in a simulator, this is a lot less straightforward. But without that modality, it's also hard to reason about the object state. So here, what we propose is to take an intermediate state to translate between the simulator modality and the real-world modality. So the real-world here we're using is an RGB camera with depth. And the simulator states we're using are something a lot more simpler, which is just the object state. And in this case, very specifically, is the center of mass of the bottle lid and the bottle body. So the way we're doing this translation is we take the RGB image, we use segmentation mask to segment out the object, and then we use depths and also an approximated center of mass of the mass to calculate the corresponding 3D coordinates in the simulator. And for the actual policy, that's the information that we feed into it. And that's how we're able to perform this central transfer. Next. So going back, yeah, that's the overall pipeline and technical challenges that we're able to resolve in this whole pipeline. And the result are these highly challenging dexterous manipulation capabilities that we got from these robots without using any human data or any real-world data. Yeah, so if you think about it, this is pretty impressive with robustness. Yeah, you can go to the next slide. Yeah, if you think about it, it's pretty amazing that you can go from zero human data, zero real-world data to this kind of performance, even achieving robustness under different kind of disturbances. Next. And all these objects shown here are also completely out of distribution, which means that these are the kind of objects that the policy during training never saw in a simulator. For a simple reason, because how do you even model a skippy bottle realistically in a simulator, right? Yeah, so we performed a lot of tests like this and found that with domain randomization, our model was able to achieve these out of distribution generalization for free, even just with simulator training. Next. And yeah, building on to the work that I just mentioned, again, we move on to another more complex platform, which is this humanoid robot, again, with multi-finger hands and 2 arms. And we applied the same principles for all the things I mentioned in physical modeling and reward design and then central transfer. And again, resolve the technical challenges there and successfully perform the central transfer without using any human data and any real-world data. So again, you can see these policies generalized to diverse objects in the real world, even though these objects are the ones that they've never seen in the simulator. And Yeah, feel free to go next. Okay, I will skip this technical part because there's the paper, and if you're interested, you can feel free to read more in the paper, and I'll just show more results on the capabilities and different generalization and robustness of the policy here. Next. Yeah, this is a bimanual handover task that was particularly difficult to reward design for because you can see a lot of contact, specifically making and breaking of contact happening here. And yeah, that's the definition of a hard manipulation task. Next. Lifting of different boxes of different weights, mass, and sizes. Next. And also grasping of a lot of different objects. Next. Yeah, so something that I found particularly interesting was that you can see how the fingers are actually adapting to different positions and shapes of the objects. So even though on the left and the right, these are the exact same objects, you can see the emergence, different grasps that the robot is actually using to handle them differently when they're in different positions. So this shows that the policy is not overfitting by just commanding a power grasp or some other kind of average grasp. It's actually seeing the environment, analyzing it, and adapting its policy online. Next. And also there's this generalization that comes for free to a lot of objects that are hard to grasp, including really small and really out of distribution objects. You can show the right-hand side video as well. Next. And again, robustness against random disturbances. All right. Yeah, so I actually tried very hard to the extent that I was really worried about breaking the robot, but again, really impressed that it was able to handle all those disturbances. And on just a technical note here, I think the robot was able to get these robustness because we're training them in the simulator, and in the simulator, we can randomize the environment by adding these random forces of different magnitude. And that allowed it to transfer the policy to a real world with the same sort of robustness. And going back to the technical challenges that I mentioned at the beginning, so learning in a simulator really offers us a good way to circumvent the hardware issues. Because as I mentioned, you just can't have the robot run and explore in the real world for free. It's going to break the environment and the hardware. But you don't have that issue in simulator. Yeah, so now that I've covered the first two parts, one on imitation learning and teleoperation, and the other one on reinforcement learning and Toru, the last challenge that I want to mention, it's very specific to robotics, is how do we actually build a continuously improving system? Next. So, I present two major classes of existing approaches. I think a lot of these robot learning works in today's literature really fall into either one of these categories. But we actually don't see a lot of them combining these two. And if you think about it carefully, I think each of these approach really has distinct advantages and also disadvantages. So for the first approach, is mostly taking a human curated data set. This allowed us to get some really impressive demos at a really fast speed, but then it's not really scalable in the long run because it's not built or less compute, as I mentioned initially. And then we have this class of approach, which is about RL from scratch, which is about how you define a static reward function, and then you learn from the reward function online, either in simulator or in the real world. But then you run into the core problem of RL, which is that it's not efficient, and being not efficient enough is a killer in robotics because yeah, data is expensive, hardware expensive, everything is just harder than things that are completely virtual. So going back to our application to robotics, the key question here is how to enable an actually scalable and efficient continuous learning loop. Can we, instead of working on these two approaches distinctly, can we try to combine them and have them bootstrap themselves with human feedback? So here I'm going to introduce an additional work. Actually, I think I forgot whether I put one or two, but we can start from the first one here, showing how we can actually combine these two in a quite elegant way. So first work I want to talk about is Hover, versatile neural whole body controller for humanoid robots. So this is different from the work that I mentioned earlier because it's complete whole body control. There's no dexterous manipulation element to it, but the same principle could transfer. So on a high level, this work is about learning a versatile whole body controller by distilling multiple specialist simulation learned RL policy into a generalist policy that transfers to the real world. And very specifically, I will just mention what this policy do. As you can see in the bottom picture, you have a humanoid. And what is not shown in the picture is that you actually have a human controller behind this humanoid. And a human controller can use interfaces ranging from VR to RGB video and other stuff. Perform some motion and get the motion faithfully translated to the humanoid. So that's what the policy does. Next. And I think what's the most elegant part, of this work to me are two things. So one, in this work, we realized that for whole body control, you can really use trajectory following along as a general reward formulation. So all these policies have been trained with data not specifically collected for teleoperation, but just a generic graphics data set where you have, for example, human walking or punching in the air or dancing or doing other stuff as continuous trajectory. And the only objective we need is for the humanoid to follow these trajectories. And that allowed us to train these diverse motions that are commonly available in daily use. And the second biggest takeaway I have from this work that I thought is really nice is how you can use an RL policy as data generators to train IL policy. And that's the bootstrapping element that I mentioned earlier. So just to zoom out a little bit, the overall pipeline of this work works like this. So first of all, you have a set of different RL policies trained with different objectives. So for example, we have the same motion of dancing or following a specific clip. And you can imagine that all these, even though all this motion follow the same trajectory following objective, the input they get can be very different. It can be, for example, if you have a VR headset, the human command is going to be hand pulses only. Whereas if you have a joystick, the human command is going to be a root velocity on the base of humanoid. However, even though there are all these commands, the way that we can train a generalist policy is that first we train RL policies separately that take in different control commands from humans. And then we distill them into the same set of imitation learned policy. So in this whole process, the role of RL policy is actually a data generator. So if you want to think about it in a more abstract way, you can think of each RL policy as your human teleoperator collecting the data for you. And once you have the data collected from this RL policy, you treat them as a data set, and then you train the final policy. Yeah, I'll just let that sink in for a bit. And then the next slide. And this is another work that takes in a not exactly the same idea, but there's also this element of how you can train the RL policy to begin with, and then use teleoperation and imitation learning on top of it to bootstrap the policy into something more powerful. So if you click on the video, you can see that. So first, we train these dexterous manipulation policy using completely RL from scratch, doing things like screw driving. And also on the right-hand side, there's this hand tightening in it. So the interesting part of this work is that even though the hand motion, the finger motions themselves are purely RL trained, the wrist motion comes from teleoperation and imitation learning. So this is another example of how you can use RL policy as a base element to generate the data for you for things that are really hard to be teleoperated. And then on top of it, you can have human control to provide high-level guidance, for example, the wrist movement and things specific to a task objective to lessen the burden on RL exploration. And once you combine these two, you basically get a more powerful policy or the data for a more powerful policy. And again, you can distribute this data or you can train this data into a more powerful policy and the loop goes on. So this is a work that we just archived a few weeks ago. And again, I won't go into the details, but feel free to check it out on archive. Next. Yeah, so now I've gone over all these different technical challenges and how different parts of my work deal with this. Next. I think I will just leave it to the audience and feel free to ask more questions. And again, thank you so much for listening.
Yeah, Toru, thank you so much. Yeah, I think it was a wonderful talk and it was, I think, really insightful. Yeah, anyone's free to come off of mute, ask a question. If you want to turn your video on, that's great too. Yeah, I'll just leave the floor open.
Hi, just a question from the last slide, mainly, because that's the most fresh part in my mind right now. But you mentioned combining two models, one trained based on the RL policy for the more harder dexterous actions, and one trained based on the imitation policy. So, are you using two separate models as well, and then combining them later?
Yeah, so the interesting thing is that maybe I'll explain a little bit more about the pipeline. So there's only one model at a time, and this is the way it works. So first, we train RL policy to perform this in-hand manipulation. And in this case, it's similar to our twisting policy, where you see these fingers moving to either twist the screwdriver or the nut. So that's one model. That's the RL model. And what we do next is that we take this RL model out, we deploy them on the real hardware, and then we try to control the wrist with teleoperation. And that will be what I mentioned about in the first part of my work. Yeah, that's not a model, it's just a teleoperation interface.
Got it. Makes sense.
And with that process, it gives us a way to collect data for a more powerful policy with both the wrist movement and the finger movement. And that's a data set that we can distribute into another brand new, more powerful policy.
Makes sense.
Yeah.
Sorry. Okay. Yeah. Thank you very much. I've got a question. So for the second part of your presentation, actually, you made mention of domain randomization. So in the simulation, the randomization is in the disturbances on the object. Yes.
Yes. So domain randomization, what I mentioned specifically was about how we deal with the robustness. And the disturbances is random forces that we can add to both the object and the humanoid robot itself. But for the whole training pipeline, we also add in other kinds of domain randomization. For example, we randomize the mass and size and surface friction of the object. We randomize the noise and observation and action. We randomize, for example, torque friction. So there are a lot of other parameters that go into domain randomization just to achieve this level of generalization.
So how do you test for robustness since all of these is already in the training? Like it's already in the training set itself, but probably there's no overfitting, but there's no robustness because this has been seen before.
Yeah, that's actually a good question, and I will try to answer it rigorously. So I think the key intuition is that, first of all, we don't have a faithful model of the world. So there's actually no way for us to know whether the simulation distribution is actually completely the same as the real world distribution.
Mhm.
And that's by definition some generalization happening there, because there are going to be objects that are not covered completely by these distribution of parameters we have in simulator, but we don't know for sure.
Okay.
But I think, again, that's also a very good point. And I think that goes into the philosophical question of what is generalization really? Because if you think about the generalization, hashtag generalization happening in large language models, personally, I think a lot of it is also overfitting. A lot of it is there is the compositionality and emergent extrapolation, but I also believe it could simply because a lot of the input data and output data already exists in the training set. And I think it's the same thing in robotics. If you think about domain randomization, you can also see as a way of covering as much of the task distribution as possible in the training distribution. Because if you just keep adding in more domain randomization, you're going to get a larger distribution of robot dynamics, of object dynamics, and there's a higher chance that your policy will be able to be sent to real transferred. But again, there's no rigorous way to test it. And we just have this blanket term called generalization to call this emergent capability.
Yeah. All right. Thank you very much. Cheers.
Yeah, thanks. Good question.
Yeah, go ahead.
Yeah, Toru. Thank you, first of all, for the great presentation. So I had a quick question from your first paper. I remember an image where you had depicted the different ways of reward functions, right? Yeah, I wanted to ask, like, on the left-hand side, that left hand, you mentioned two reward functions. So is it like those two reward functions are very localized to the left hand only? Or is it like, will it work the other way around as well? What I mean is,
sorry, which
is
work was? I think I'm a little bit lost. Which work and which specific reward function are referring to?
Yeah, it's the first paper. So maybe if we can go there.
This one?
No. This one, but not this page.
This is the first one, I believe.
This one?
No, go ahead, maybe.
I think this is the first one that
Yeah.
I
No,
mentioned.
it was that twisting hand, that one.
Okay.
Oh, okay. And then it's the first one in the RL part.
Yeah,
this one.
this one. Yeah, so you can see how the loss functions here for the left hand is like, it says, okay, the left hand reference contact points. So is it like the left hand only holds the object and the right hand only rotates the thing to open it? Or can it work the other way?
Yeah, so in this case, we specifically define it this way because we design our real hardware setup to perform the task in this way. But because everything it's just a matter of symmetry. So you can flip the whole thing. You can change the left hand reference contact points to the right hand and vice versa. And then you can switch the orientation of the bottle. And that's actually something that we've tried, and the policy just works as beautifully.
Oh, so it can work the other way around.
Yeah. So if you just flip everything around, basically this underlying principle is completely the same. The training process is the same. And if you just run a training, the model will learn to perform the same thing, but in an opposite direction. And something interesting that I want to mention is that we also try changing the magnitude of the rotation reward. So by doing that, we can also control whether you're twisting close or open the bottle leg. because it's basically a matter of changing directions.
Okay, cool.
Yep.
I had one more question from the second paper, which was probably the next one. Okay, maybe this one. So this dropping of object, right?
Mm,
Let's say that person, that robot, it's dropping an object into a certain space, right?
mm.
Let's say that basket.
Yep.
So will it be able to take care of it if, let's say, the basket is mobile, the basket is moving, let's say?
In this case, no, because it didn't appear in the training task. It will be an
Yeah.
interesting, it will be an interesting task though, and I can imagine you need to do some work in setting up the simulator environment. Yeah, so I can imagine you can have something like a car, a moving object in a simulator, and then maybe your objective will be the same. Like instead of chasing a fixed goal position, you're chasing a moving goal position. And the training will probably be harder, but I think it's also doable.
Yeah, so it will
Yeah, it'll
probably
be
be something like, sorry?
it'll be an interesting task to try.
Yeah, it'll probably be something like where it has to think ahead of its time, and we'll have to maybe predict a projectile.
Yeah, I think the key bottleneck in that case would actually be the hardware performance. So for this, we're running everything in 10 hertz. And I think it will probably be a max of 20 hertz because first of all, the perception pipeline actually runs fairly slowly. And also the robot controller, if you run it at a higher speed, is also easier to get overheated and just cause dangerous movement. So I think in theory, that task is possible. In practice, it would just require more engineering work.
Yeah.
Yeah,
Okay,
but it's
cool.
very interesting.
Yeah, thanks for your time.
I had one quick follow-up on that too. So this specific work for the sim to real reinforcement learning vision-based dexterous manipulation, this is also RL in sim, correct?
Yep.
Okay.
Yep.
So
Completely.
yeah, so one question I have is like how much randomization did you do for object placement, like initial object placement? I think one thing I've found working with the research group I work with is that even sometimes generalizing some of these grasp poses just by moving the object to different places on the in the like on the desk here or on the table here introduces like reasonable challenges
Really interesting. Yeah, so I think for this, I have a very specific set of numbers. So I think it's about 20 centimeters in x-axis, about 10 centimeter in y-axis, and about 10 centimeters of variation in z-axis. And those are very specific numbers because it's also related to the workspace of the robot. Because you can imagine if we try to set a goal position that is too far away, the arm simply cannot reach it.
Right.
And that will disrupt the RL training.
Right. And these are Fourier robots, right? Typically it's just the upper body.
Yep.
Yeah. I'm curious if you ever tried like a cross body placement. So left arm reaches across to the right, even though it's in its workspace, but the right arm is closer. I'm just curious.
Yeah, I did not think about it because it was just very unnatural. But I think it's possible. I think the bigger concern I had at that time was for this model, we did not really factor in the possibility of collision, including self-collision. So I just wanted the motion to stay as far away from any self-collision as possible. So I did not try that.
Yeah. These are expensive, so I get it.
Exactly. I didn't want to break it.
Yeah.
Maybe I could ask one more question.
Yeah.
So for the collision, actually, the collision avoidance is in the robot itself and not in your reward function. Yes, this is what you mean.
No, exactly. So I think there's only self-collision penalty for the sake of like not well, in simulator it's more about penalizing your robot such that it gets to the correct goal state faster. It's about performing the task. But there isn't an explicit concern of safety during the training process. Because I imagine if you want to factor in your simulator training, then it will be engineering-wise, it'll be harder because you might want to calculate, for example, the velocity at which you're hitting a robot and the possible damage it causes, and the magnitude of force, and so on and so forth. Yeah, so I did not really use any of those information during training. And as a result, it doesn't really learn to safely protect itself against collision.
So it's just you try to do this by making sure that, like in the mechanical setup of the robot, it doesn't happen. This is what you did, yeah.
Yeah.
Great. All right. Cheers. Thank you.
Thanks.
We probably have time for maybe one more question if anyone has one. So like 10 seconds to ask. If not, we can wrap up.
Hey, one last question again. Yeah, so this is something of a survey I'm doing with every researcher I meet. It's like with all these top models accessible to everybody, what does your daily coding tech stack look like? And like what fraction of your daily code do you write manually and what percentage of your code does AI write for you?
Sorry, what's the first question again?
Yeah, like not to overcomplicate it, but like what fraction of your code every day is written by AI?
I said I think the other part was what's your coding tech stack.
Oh, I see. It's my hand and my brain. VS Code. Well, to be fair, I think when I work on this project, cloud wasn't a thing yet, and I was very late to the party, which I regret actually. Nowadays, I use cloud a lot, but for this project specifically, it was my hand and my brain and my VS Code, and maybe autocomplete.
Oh, that's nice to hear. Yeah.
Well, yeah, good last question. Toru, thank you so much for joining us, and thank you everybody for the good questions. We'll have another session in another couple of weeks, so stay tuned in the Cohere Labs Discord group. And yeah, if anybody's interested in connecting with Toru, just reach out to me and I can connect you, and or you reach out to her directly, either way. But yeah, everyone, thank you so much for joining. Toru, thank you so much for your presentation. It was super insightful.
Yeah, thanks for resolving the technical challenge.
Hopefully there weren't too many nexts that you had to say.
Yeah. Yep. Thanks. Have a nice day. Bye.
All right.
Yeah,
Thanks all.
Toru. Bye.